Okay, so let me quickly refresh you the memory. So we're looking at the Cauchy problem for the Einstein equation. So here I have my Lorentzian manifold, which has dimension 4. G is Lorentzian, so it has signature minus plus plus plus. And we're looking at the Einstein vacuum equations, which correspond to a manifold, Lorentzian manifold with a vanishing Ricci tensor. As we have seen, this corresponds to an evolution problem. And for this evolution problem, the Cauchy data set is the triplet sigma naught, G naught, K, where sigma naught has dimension 3, G naught is Riemannian, and K is a symmetric to tensor. And then solving the Einstein equation means to solve Ric is equal to 0 such that sigma naught is a space-like hypersurface of your manifold, G naught is the induced metric, and K is the second fundamental form. Okay? Well, okay, so for the experts, you know that there are also some compatibility conditions known as constraint equation that G naught and K have to satisfy, but for now, I might have to talk about it, but for now, let me just not talk about this. And the question we have here is the one of local existence. And more to the point, I'd like to ask how rough can the initial data be in terms of regularity, actually subway space regularity, so that we can give a sense to these equations, so we can prove local existence. And here, as I promised in the first lecture, I'd like to motivate first, before stating the result I want to present in the rest of the lecture, I'd like to motivate why it's interesting to look at rough local existence is important for the Einstein equation, or more broadly for evolution PDEs. So we have seen one example this morning for the Yang-Mills, where if you are able to prove a well-posedness at the level of the energy space, this immediately gives you global existence. And here I'd like to give another example, which is more in connection with the Einstein equation. And for that, let me first review what is the weak, so-called celebrated weak cosmic censorship of Penrose. So this starts with the basic observation that there is a very well-known solution I did not talk about, which is the Schwarzschild solution, but which you probably know, which has a singularity. It's a spherical symmetric solution which has a singularity at r is equal to 0, okay, in the spherical coordinates tr, theta, phi. And this singularity, well, of course, I'm not a physicist, but I guess that from the point of view of physics, singularities might be undesirable, in the sense that you might think that physical theory breaks at that point. And therefore, you'd like to know if a solution like Schwarzschild, or if singularities in general of space-times are a limit to the physical theory, or at least should be seen as undesirable. And the answer is that this should be a problem only if you have access to observation of the singularity. And the point is that, in particular, if this singularity is as in the sorry. Let me just remove this. Okay. If this singularity is inside a black hole, essentially, so a black hole is a region you don't have access to by observation. For an observer near infinity, since the light rays are trapped in the black hole, you don't have access to whatever is happening in the black hole. So if the singularity is hidden in the black hole, which is the case in Schwarzschild, then this should not be seen as a problem, because you simply don't have access to observation of the singularity. Okay? And this led Penrose to his celebrated weak cosmic censorship in 1969, which is that singularity are generically hidden by a black hole. In other words, the situation of Schwarzschild is the generic one. It's not an exception, it's the generic situation. Of course, I have to put generic here because there are known counterexamples, but they are believed to be non-generic precisely. They are believed to not survive to perturbation, to small perturbation, to arbitrary small perturbations. Okay, so let me give a slightly more precise statement. So you might prefer the following statement. For generic, asymptotically flat initial data, the maximal Cauchy development of the corresponding solution to the Einstein equation has complete future null-infinity. So if you understand this statement, it's good. If you don't understand, then you might prefer that one. It's the same thing. I mean, it just essentially says the same thing. Okay, but here there is one word which is very important in this statement, is precisely the word generic. Okay. In other words, since it's not for all perturbations, we'd like to say that it's for almost all perturbations, and the idea is what is the sense of almost all. And here, the idea is what is the norm in which you should measure your perturbations. In other words, there are known singularities, I mean, what are called naked singularities, that are singularities not hidden by a black hole. And you'd like to say that they do not survive arbitrary small perturbation, but then I have to tell you in what norm I measure smallness of the perturbation, of course. And of course, here we have infinite dimension, so the topology is, there's a difference. Different norm give you different topologies. So genericity depends on in what norm you're going to measure your arbitrary small perturbation. Okay. So why is this related to our problem? Well, simply because obviously my perturbation needs to be small because it needs to be arbitrarily small. But on the other hand, it needs to be large enough so that when I perturb my naked singularity, I suddenly start seeing a black hole around it. So it needs to be large enough to generate a sufficiently large deformation of the space-time to create a black hole. But at the same time, it needs to be small enough because I said it's arbitrarily small. And of course, the best way to do this in infinite dimension is to take a very rough norm, because a rough norm, if you measure a perturbation in a rough norm, it may be small in the rough norm and yet large in a smooth norm. Okay. So that's why it's certainly a hint that you might like to have rough norms. Okay, and so let me be now more specific and show you an example where this conjecture has been solved. A particular case where you will see that indeed you need to have rough norms if you are to prove this conjecture, which is very important to the field. So here let me mention, if you heard about the strong cosmic censorship, so there's also a strong cosmic censorship, but they are not, they are related, but it's not like the strong one implies the weak one. It's just there are two very important conjectures. Okay, so there is a particular case where this has been solved by Christodoulou in 1999, and where, as we will see, it's very important precisely to have a rough local existence result. And that's the case of spherical symmetry. So as you may know, in spherical symmetry, the equations are non-dynamical. If you take the Einstein vacuum equation in spherical symmetry, by Birkhoff's theorem, there is only one solution, that's the Schwarzschild family. So it's not a dynamical equation, it's rigid. But if you couple the Einstein equation to a matter field, it starts getting back again dynamical. So the easiest matter field is the scalar field. So you couple the Einstein equation with scalar field, you reduce the symmetries by looking at spherical symmetry. And it turns out that then you can prove that indeed weak cosmic censorship holds in this case. Again, that's a celebrated result due to Christodoulou in 1999. I mean, it's a series of papers which culminated in 1999. And here there are two main ingredients of the proof. I mean, of course, it's a long proof, and it's a very beautiful proof, but let me just summarize it in 2 points. One of the main ingredients is precisely a very rough local existence result, and I'll be a bit more precise here. And the other one is a sharp criterion for the formation of so-called trap surfaces. So actually what's happening is you take a space-time with a naked singularity, and instead of proving that a black hole forms, you're going to perturb it and show that with arbitrary small perturbation, you form a trap surface around the singularity. So that it's, again, a trap region means precisely a region which is hidden to observation because it traps the light. Light cannot escape from it. Okay? But anyway, okay, so it turns out that it's enough for getting the result. And so here the idea is that to obtain a trapped surface using this sharp criterion that I mentioned here, one needs perturbation of the initial data set with a jump along the backward null cone from the singularity. Okay, so you take you take a space-time with a naked singularity. So let's say that this is my singularity. I draw a backward null cone from it, and then I'm going to consider a space-time where I'm going to add an arbitrary small perturbation here. And this small perturbation is going to propagate along the backward null cone. And the idea is that then, as it propagates, it finally forms a trap surface. So that's the trap surface. and that's the singularity. Okay, so no matter what is a trapped surface, I'm not going to talk about it at all in this talk, but turns out to be enough to get the solution. The important thing is that to be able to generate this trapped surface, it is absolutely crucial that you allow for perturbations with initial jump along the backward null cone. So in particular, it's a very rough solution, and it's actually as rough as it gets. You can't make it any rougher than that. And the idea, many directions now in GR nowadays are extensions precisely of these two ideas. Try to extend these ideas to non-spherical symmetric cases. Okay, so clearly you want to, in particular, there is this iterating result of Christodoulou of formation of trapped surfaces in the non-spherical symmetric case, which has had lots of impact and further works on this. And so this is one direction, and the direction I want to talk myself here in this lecture is the other direction, the one of trying to make sense of very rough solution to the Einstein equation, possibly as rough as possible. Okay, so here I should mention that, however, for the proof, we cannot be inspired by this rough local existence result of Christodoulou, because in spherical symmetry, you are in 1 + 1 dimension, essentially, and this is a very different world from higher dimension for hyperbolic systems. So here he relies on BV spaces, which are totally inadequate for higher dimensions. So we have to rely on Sobolev regularity. So, we'll have to find a totally different proof, but nevertheless, it's important to understand that for this very important particular case, he had to rely on very rough solution. He could not do without. Okay? So that's another motivation, this time in connection to the Einstein equation. I hope that I convinced you that making sense of rough solution is actually an important issue. And this brings me to the result I want to talk in this lecture. So finally, I get to state it. So again, so I call this the bounded L2 curvature theorem. So it's a joint work with Kleinemann and Rodzinski, and it states the following. So you take an initial data set, sigma naught G naught K, with curvature. So here it's the curvature tensor on sigma naught. So it's the curvature tensor on your three-dimensional manifold. So it's the induced curvature tensor if you want. So the curvature tensor is in L2 of sigma naught. Actually, in dimension 3, it's equivalent to saying that the Ricci tensor is in L2 of sigma naught, but anyway. And so the curvature tensor is in L2 of sigma naught. And I also have, so that's the assumption that you have on G naught, right? And then the assumption you have on K is that the first covariant derivative, so that's the induced covariant derivative of sigma naught. So the first induced covariant derivative of sigma naught of K applied to K is also in L2 of sigma naught. Okay? And then the Einstein equation are well posed. Okay, so let me do several comments here. Well, first, obviously, there are other assumptions to this theorem. In particular, I talked a little bit about, there was the mention of asymptotic flatness. I mentioned also that you have to satisfy the constraint equation. So, there are other assumptions, but let me just mention the ones that are relevant in terms of regularity, which are these two assumptions here in red. These are the ones that are relevant in terms of how low the regularity is in your assumptions. You also have to assume a lower bound on the volume radius, but let me also not elaborate on this. Okay. Well, the other remark I want to say is again in connection with what I said this morning. As I said, this is at the level of the metric in H2, right? Because the curvature tensor here in a coordinate system gives you two derivatives of the metric. So this is at the level of two derivatives of the metric in L2, which is at the same level as the Sobolev space H2. And same for that assumption here. Right, the second frontal form is at the level of one derivative of the metric. So here you're again at the level of two derivatives of the metric in L2. Okay, so the two assumptions here in red are the same level of regularity, that is curvature metric in H2 or curvature in L2. Okay, so let me give some motivations for these results. We saw already some of them, but I'd like to come back on it. So one motivation is in connection with the lecture of this morning. That's in connection with well-posedness for quasi-linear wave equations in general. We have seen that the Einstein equation in coordinate system takes the form of a quasi-linear system of a system of quasi-linear wave equations. And here in this framework, remember that the best result known so far is the result in H2 plus epsilon of Kleinemann and Rodiansky for the Einstein equation, and Smith and Tataru for the general quasi-linear wave equations. And here I'd like to point out that with respect to these results, it's, this result, of course, in some sense, you could say you just go from H2 plus epsilon to H2. But the point is that, remember, this is a very, it's not about the technical improvement, it's a very different proof, right? The proof I mentioned for H2 plus epsilon relies on Strickhaus estimates, and as we have seen this morning, it's an optimal proof within that framework. So here, as we'll see, we'll have to, first of all, we'll have to exploit the full nonlinear structure of the equation. So here the structure becomes important. That's, I guess, the main interest of this result is that you do have to dig deep in the structure of the equations on the nonlinear structure. And the other thing is that you rely not on Strickhaus estimates, but rather bilinear estimates here. So it's really a different technology. Okay, so now I'd like also to talk about, more specifically, about the way we state our assumptions. There is something nice in terms of the assumptions here, is the fact that both assumptions here are invariant. Okay, so the curvature tensor is invariant. So invariant means that you do not need to refer to any coordinate system to state them. Okay, so the curvature tensor is certainly invariant, the L2 space is invariant, and the covariant derivative is invariant. So here all these objects are invariant. In other words, these assumptions do not refer to a specific coordinate system. They are independent of any reference to a coordinate system. So why is this important? Well, simply because there is this very large gauge invariance of the Einstein equation, which is the choice of gauge or of coordinate systems, if you want. It's a bit more general, but let's say coordinate system for simplicity. And because you have this freedom of picking any coordinate system, then you'd like to have a framework. So this local existence result is a framework within which you work. You'd like to have a basic framework where you keep this freedom, okay? And therefore, I don't want of a local existence result which ties me to a particular coordinate system, because then the only thing I know is that within this coordinate system I propagate the regularity. I have no knowledge of whatever happens in another coordinate system. So in particular, that ties me to a particular coordinate system without the freedom of switching to another coordinate system. So I'd like to retain that freedom, and certainly this statement allows you this because it's invariant under the choice of coordinate. I do not refer to a particular coordinate system. And you see in particular, this is not the case of the result in H2 plus epsilon, because there is no invariant definition of H2 plus epsilon. You'll have to go to a coordinate system in which the coefficients of the metric are in H2 plus epsilon, and then you will be tied to this coordinate system. In particular, the proof of Kleinemann and Rodiansky uses wave coordinates here. And now there is a more recent proof of Qian Wang that we prove this result in another gauge, I think CMCSH gauge. Okay, I'd like to talk about now breakdown criterion, because another thing that local existence result tells you for rough data is it tells you about breakdown criterion. In other words, it tells you about how much regularity of the solution you need to control it. Okay, so here what I mean is that this result as a byproduct tells you something about smooth solution and not only rough solution. And why is that so? If I start with a smooth solution, let's say a classical solution, and I like to know for how long does it stay smooth without seeing any singularities, then you don't have to check that all derivatives of the solution stay under control. The only thing you have to check, this result tells you, it's not only a wave coordinate result hidden here in the statement. There is also a statement about propagation of regularity, which tells you that if you start smooth, you stay smooth as long as curvature is in L2. So in other words, if you want to know if you stay smooth, the only thing you have to check is curvature in L2. So that tells you that curvature in L2 is a fundamental quantity controlling singularity formation. And again, in connection to breakdown criterion, so first of all, the breakdown criterion that you deduce from this well-possessed result implies all previously breakdown criterion derived for the Einstein equation. But furthermore, it also, more to the point, it also tells you the fact that it is invariant, again, that it only involves the curvature tensor, which is invariant in the L2 space, tells you in particular about true singularities and not coordinate singularities. So it's a breakdown criterion which tells you not about coordinate singularities, but true singularities. So that's another advantage. Okay, so I want to give a last motivation. So far I talked about the fact that it's a simple criterion and it's an invariant criterion. But now I'd like to ask the question whether it's as simple as it gets. Can you have a even simpler criterion? Okay, because remember the proof of Christodoulou in spherical symmetry, it's actually important that he gets a well-possessed result which is as rough as possible. So here, I'd like to mention that, at this stage, we don't know if this result is optimal. Okay? However, there is some criticality in this problem, which hints towards the fact that if you are to beat this result, then you'll have to, I don't know, really come up with something totally different in the sense that you reach criticality in this problem, and this could point towards optimality of this result. And the criticality is best seen by considering an equation we will see, we will focus on in the third lecture tomorrow morning, which is the Econal equation. Okay, so the Econal equation is this equation here. So here, assume, to understand this point, assume that you have already constructed the spacetime. I think it's easier to understand. So assume that you have constructed the spacetime, and you suddenly want to control this equation, G alpha beta, D alpha U, D beta U is equal to 0. Then, as we will see in tomorrow morning's lecture, it turns out that it is critical that you control the curvature tensor in L2. Okay, if you don't control it, even controlling the curvature tensor in L2 is barely sufficient, and you have to heavily use the structure of the Einstein equation. But certainly, you could not control this equation. I could not make sense of this solution without having curvature in L2. So, of course, you could tell me, why you care about this. The point is that the Econal equation. So there are two considerations. On the technical point of view, as we will see, the Econal equation is fundamentally tied to representation of the wave equation. Okay, when you take a representation formula of the wave equation, like the plane wave representation or any other one, it's always connected in one way or another to in a fundamental way to the Econal equation. The Econal equation, the solution of the Econal equation, is the main building block of any representation of the wave equation. And in any hyperbolic problem, if you do something refined about this equation, you will need a representation formula, and hence you will need the Econal equation. Okay, so on a technical level, experts know that this is fundamental, but of course on a more basic level, if you look at the level sets of you can actually, the null hypersurfaces of your spacetime, in particular the light cones, can be obtained as level sets of the Econal equation. So in other words, if I don't know how to make sense of that equation, I don't know how to make sense of light cones or null hypersurfaces. Okay, and as far as light cones are fundamental in both in Lorentzian geometry and in Einstein equation, in particular in Lorentzian geometry in general, it's hard to believe you could do anything meaningful for this equation without making sense of the light cones. Okay, but again, let me mention that, of course, this is just speculation. It is open to know if this result is optimal. There's no known counterexample or example that go below so far. And that would be, of course, certainly a very, both, either an example or a counterexample would be great. Okay, so now let me talk about the strategy of the proof. Okay, so in view of what we have seen this morning about the seminar case, at least the first 2 points will seem very natural for you. So the first point is about trying to uncover the null structure of the Einstein equation. Okay, as we have seen, the Einstein equation take the form Ric alpha beta is equal to 0, and this form is quite mysterious. Even this morning, to show you that it was an evolution problem, I had to resort to a particular gauge, which were wave coordinates, because in this form it's a bit untractable. So here we know that we need a kind of null structure because we know that this result is not true if you don't exploit the structure. So we need to uncover the null structure, and certainly it's a bit mysterious in this form. So we need a gauge which allows us to see the null structure. And it's natural, in connection to what I said this morning, that we can find a gauge in which we see the null structure in the sense that we get a quasi-linear version of the classical Young-Mills theory. Okay, so remember this morning I talked about classical Young-Mills, and I showed that it has the null structure at least once you pick the right gauge. And here we'd like to argue that a very good way to see the null structure in the Einstein equation is precisely to be able to pick a gauge which reduces the structure of the equation to a quasi-linear Young-Mills theory. So what I mean by this is that we will obtain the same structure, formal structure, as the one we had for Young-Mills this morning. The only difference is that instead of being set on the Minkowski spacetime, which is a fixed background, now it's going to be set on the solution of the Einstein equation, which is the unknown of the problem itself. So you don't have a fixed background, you'll have a background which is the unknown of the problem itself, so that's the quasi-linear feature of the Einstein equation. Okay? The background is never given, you have to construct it. Okay? Okay, but anyway, we'll see that we get something which has the same structure, but in a quasi-linear setting. So that's the first step. So the first step is about uncovering the null structure. Once we have this null structure, then the next step is to exploit it. And as we have seen from the seminar case this morning, the way to exploit the null structure is to use so-called bilinear estimate. Now remember that the linear estimate You will have, if in other words, you will have yeah, maybe I can already write it. I mean, you will, at the end of the day, thanks to your Yang-Mills formalism, as we have seen this morning, you can reduce everything to a system of wave equation. So let me just write a quaternion version. So, sorry, a scalar version. So you will reduce your system to scalar wave equation of that form. So you have, I mean, roughly. So you have a derivation G of phi is equal to Q of phi phi, while Q is a null form. And again, the difference is that you don't have the flat derivation, you have derivation on the background, which is the solution of the Einstein equation. Okay? So once you have done this, you'd like to estimate the right-hand side here, and that's where you need the bilinear estimates. And remember that a bilinear estimate consists in estimating the space-time norm of this term here, but by not breaking it in the product of two norms using functional analysis, but by really exploiting the structure of the product. I mean, you really estimate the product and not the. Okay, so that's bilinear estimate. So that's how you. So in some sense, after A and B, the proof is over. In the sense you uncover the node structure, you exploit it, and then there's nothing left. Okay. However, there are still 2 points because of the fact that here to prove these bilinear estimates, you need to rely on a representation formula. In other words, you need some kind of plane wave representation of your wave equation to be able to prove these bilinear estimates. And therefore, you need to construct this plane wave representation, which I'm going to call parametrics. So that means you're going to simply have a representation formula, which is an approximate solution to this equation derivation G of phi is 0. Okay, it's going to be a plane wave type representation, but in a curve setting. And not only you have to construct this approximate solution, this parametrics, but you also have to control it, and in particular control the fact that it's not an exact solution, but not an approximate one. So you need to control the error term which is generated. And finally, once you have done this, it turns out that in these bilinear estimates, as we will see in the second hour of this lecture, some bilinear, there are 2 types essentially of bilinear. I mean, there are lots of them, but they essentially come in 2 families, which corresponds to the 2 bilinear estimates we saw for Yang-Mills this morning. And for one of these 2 estimates, we need to, in addition, we need to prove a sharp L4-Strickhardt estimates for the parametrics. Okay, so what I call sharp L4-Strickhardt estimates is you need to prove the same L4-Strickhardt estimate as for the flat wave equation, which is the following. So in this case, it will be for a curve equation. So you want to prove that if derivation phi is equal to 0, then basically you have, well, let me do it for the flat case, and then we'll do it for the curve case, but it's easier to state. So you want to prove that phi L4 spacetime is controlled by phi 0 in H 1/2 dot plus phi 1 in H minus 1/2 dot. Okay, so why do I call it sharp? Because that's exactly the one you have in dimension 3. If you come back to, let me quickly come back to the Strickhardt estimate. So here, this corresponds to taking P is equal to Q is equal to 4, in which case you can easily check that R is equal to 1/2. Okay? So that's the sharp in the sense that you have to prove in the curve setting and in the rough background the exact same statement you have for the flat wave equation. Sorry, no, here, okay. Okay, so these are the steps we're going to consider. So I'm not going to go in this scheme linearly. I'm going to tell you in the next slide how we proceed. But before I'll review all these, some ideas of these steps, the main ideas of these steps. Let me first again emphasize the fact that the difficulty here. So step A is essentially algebraic, right? The reduction here is algebraic. But step B, C, and D are about proving estimates. And in this business, whenever you prove estimates, your main constraint is that you can only assume L2 bounds on the curvature tensor. Okay, so that's the main constraint. You want to achieve step B, C, and D. So you're in the framework of a big bootstrap, and the bootstrap information you have is that you can only assume L2 bounds on curvature. And the other thing is that again, this scheme only works because because you're able to exploit the full structure, a null structure of the Einstein equation. If not, if you don't exploit it, the proof is wrong. I mean, it's going to collapse. It's only true at this level of regularity. It's only true because there is a special structure. So that means you have to exploit it. And the interesting thing is that you not only have to exploit it here at the level of these Balian estimates, but you actually also have to exploit it in particular to control the parametrics. I mean, the structure comes all over the place. Maybe not so much in the last step, but certainly in BNC. Okay, so let me give an overview of the remaining lectures. So here in the end, I mean, in the remainder of this second lecture, I'll give an overview. I'll give a quick overview of the proof to have to see exactly how these ideas fit. In particular, I'll talk about this Yang-Mills formalism. Then in the second hour, I'll talk about bilinear and Strickhart's estimates, how you prove this on a curved background. And then I'll focus in the two last lectures. So tomorrow morning, I'll focus about this Econal equation, which again is the main building block of any representation of the wave equation, actually, at least any known. So for us, it's going to be the main building block of our representation formula. So I'll talk about the Econal equation, and in particular how you control it when the curvature is in L2, when you have a very rough background, and how you get the most out of it in some sense. And then in the fourth lecture, it will be about the control of these plane wave parametrics. So in particular, these parametrics, we'll see that it's a Fourier integral operator, and we'll try to see how to control this Fourier integral operator on a curved background with on a curved and rough background. Okay. Okay, but here for the rest of today's lecture, let me give you an overview of the proof of the Bandé-Deltour curvature theorem, and let me focus on bilinear and Strickhart's estimates in the second hour. Okay, so let me start with this Yang-Mills formalism I was talking about, which is the way you uncover the null structure in the Einstein equation. Okay, so you'll see that it's very, will indeed be in the same framework as this morning. So you pick, so the way you do this, you take the Cartan formalism for moving frames. That is, you take an orthonormal frame, which is your unknown if you want, and so it's orthonormal in that sense, of course, because you're in Lorentzian geometry. So G E alpha E beta is M alpha beta. And you consider the connection 1 form associated to your frame. Okay, so A mu alpha beta. So here I have three indices. I'm going to separate between mu and alpha beta in the following sense. So you have A mu alpha beta is G of d mu E beta E alpha. So it's the usual definition of a connection 1 form associated to a frame. And here the mu index is the important one here, is the one along which you differentiate your frame. And alpha beta, let me see it as external indices. I mean, they are not so important, but of course, if you separate mu from alpha beta, you see that you are in the same framework as this morning. This morning we had a connection 1 form from a space-time with values in a Lie algebra. And here, of course, you can see that because it's an orthonormal frame, and because the covariant derivative does not see the metric, this is antisymmetric in alpha beta. So you see that you have a 1 form with values in antisymmetric matrices. Okay, so that's why I said this morning that the main example for us for Yang-Mills is the case of the Lie algebra being a little SO31. Okay, so you have exactly as this morning you have a connection 1 form. This time not from a flat background, but from the curved background, which is our unknown of the Einstein equation, with values in antisymmetric matrices. Okay, so now I'd like to recover. I would like to recall the link between the curvature and the connection because as we have seen this morning, there is the same link for the Yang-Mills. So remember that when you have a connection, you have a relation between first order derivative of the connection and the curvature tensor, exactly as for Christoffel symbols if you're in a coordinate system. And more particularly, you have R alpha beta mu nu is d mu a nu alpha beta minus d nu a mu alpha beta. And then you have this quadratic term with a very special structure, which is actually a Lie bracket. It's our definition of the Lie bracket on antisymmetric on little SO31. Okay, so now I'd like to use the fact that I satisfy the Einstein equation. I mean, I need to use the equation here somewhere to derive my Yang-Mills formalism. And the way I'm going to use it is I'm going to use consequences. So I talked about the so-called second Bianchi identities satisfied by the curvature tensor. So I'll say a bit more. So in the third lecture, I'll come back to this and I'll write them down. when I talk about the economic equation. So for now, let me just say that with these symmetries called the second Bianchi identities and with the Einstein equation, as a consequence, when you contract the Bianchi identities and you use the Einstein equation, you get the following formula, which tells you that the curvature tensor is divergence-free with respect to the third index, and it's actually, due to the symmetry, it's actually divergence-free with respect to any index. Okay, but so here, let me just use that. Here, it's a divergence between, because I'm contracting here, you have the mu and the mu, which are contracted, so it's divergence with respect to the third index. So let me just, it's with respect to any index, but let me just use this formulation here. Okay, so this is a consequence of the Einstein equation. Now I want to use this to derive an equation for the connection one form. Okay, so you take d mu on this side. So d mu r mu is 0, so the left-hand side is 0, and you look at what you get on the right-hand side. So first of all, you get d mu, which is the covariant wave operator. So that gives you D'Alenvallian G of A nu. Then here you have d mu A mu. So here I can commute, right? And that would be d mu A mu. And that would be d mu, so that's the, sorry, d mu A mu, okay? And that's the space-time gradient of the space-time divergence. Okay, so here, of course, everything is with respect to covariant derivative on my space-time. And then I generate two terms. The first term is the one I get when I take, I also have I differentiate this Lie bracket here, and that gives me d mu of the Lie bracket of A mu A nu. But I also commuted two derivatives, and because I'm commuting d mu and d nu, I get a curvature tensor. So I get a term of the form A mu times the curvature tensor, which I do re-express in terms of derivative of A. And of course, because I do this, I pick up extra cubic term, which comes from this applied to A mu. Okay, so I pick extra cubic term. But as I said this morning, the cubic term are low order because you just treat them by Sobolev. So they do have actually also a structure of the cubic terms, but I'm not going to use it here. Okay, so. No, you need to, so partial mu only works with a coordinate derivative. So, so if you have coordinate derivative, you can replace partial with covariant, and then you do everything with covariant. It is a connection, yeah. You apply a covariant derivative to one form, right? But it's just that if you express it in coordinates, it's the usual thing that a curl does not depend on the, a curl does not depend on the connection, right? So the curl you can simply express it like this, but this turns out to be equal to. This is the same thing as if you replace with covariant derivatives, and that's what you do to get your equation. Okay, so you get, nevertheless, so you get this equation. Again, the cubic term, I don't care, but you can see already that you get exactly the same structure as in Yang-Mills. You get the covariant wave operator here. You get the space-time gradient of the space-time divergence, and you get quartic term with a very special structure, and then you get this cubic term, which I'm not going to mention. And clearly, this is the exact same structure as in Yang-Mills that we saw this morning. The only difference with this morning is that, of course, now everything, every covariant derivative is not in Minkowski. Now it's not on the Minkowski spacetime, it's on the curve background, which is the unknown of the Einstein equation. So it's on MG. Okay, so that's why I call this, because it has the same structure, it's an analogous of Yang-Mills, but because it's not on a fixed background, but on a background which you're trying to construct, this is a quasi-linear version of the Yang-Mills theory. Okay, it's a quasi-linear analog. Okay, so now I'd like to perform essentially the same manipulation. Okay, let's take as what we did this morning on the classical Yang-Mills, the similar case. Let's take it as a guideline to what we want to do now. So what we did two things this morning. Actually, we did 4 steps, but let me first start with the first steps. So first of all, remember from this morning, there is a gauge invariance at the level of the connection. So you'd like to pick a particular gauge. And as this morning, I'm going to pick the Coulomb gauge. So again, this is the covariant derivative in space-time. So yeah, sorry, maybe I should say the following. So again, I'm assuming that I have a foliation. So I have a foliation by a time function Okay, and here my frame E naught, my frame is adapted to this foliation, or rather the foliation is adapted to the frame. So you have E naught here, and then here it's E1, E2, E3. Okay, so in other words, E1, E2, E3 is a frame of the tangent space of sigma t. It's an orthogonal frame on sigma t. And yeah, and what I call this is the induced covariant derivative on sigma t. Okay? So now you'd like to do, so you pick the Coulomb gauge, meaning that you take covariant derivative Aj to be 0, okay? And now there are two things you need to know first, to do first. Remember, there were two steps which are, I mean, essentially totally trivial this morning, but that now are not trivial in the curve setting, is the fact that now I'd like to scalarize this equation first, because it's a tensorial wave equation, and I don't know what to do with it. The only thing I can deal with are scalar equations. So I need to scalarize this tensorial equation, and I need to project it on divergence-free vector field to kill this dangerous term here. Okay, and the difficulty compared to this morning is now that both operations are highly non-trivial because they don't commute with the covariant operator. Okay, so so obviously I'm going to scalarize using my frame. I have a frame, so I'm going to use it. But if I scalarize, it doesn't commute with the wave operator, unlike the flat case. And same thing, the projection on divergence-free vector field does not commute with the D'Alembert on the curve background. Okay? So in other words, both commutation with the D'Alembert are going to create me additional term. And the problem is that any commutation with the D'Alembert creates dangerous term in the sense that it creates terms of the form ADA, which are the dangerous term here. So it creates a whole host of new quadratic terms, and you have to check that they all satisfy the null structure. So here, it's just about belief, right? You pray that it's going to work, and it turns out that because of the magical structure of the Einstein equation, it does work. There are lots of terms where you check them one by one, they all satisfy the null structure. Sorry? Which one? This? No, it's not equivalent. It's a consequence, right? You use Bianchi identities. You contract once the Bianchi identities, and once you contract once, you have terms involving Ricci tensor which are 0 by the Einstein equation, and the only thing that's remaining is this. So it's a consequence of the Einstein equation. It's not equivalent, but it's a consequence. Yeah, so this is right. So I take my orthogonal frame, and because of the Einstein, as a consequence of the Einstein equation, I get this equation, which propagates my frame. So I get a propagation equation on my so the propagation of the frame, or rather of the one connection one form, is given by this system, which is of Yang-Mills type. No, I am right. If my reversely, if the connection one form satisfies this equation, if the connection one form satisfies this equation, then the corresponding curvature tensor given by this formula satisfies the Einstein equation. It's equivalent if you want. Okay. Okay. So once you have performed this procedure, you have reduced yourself to a scalar wave equation, which is what you want. Rather, it's a system. As we have seen this morning, it's actually a coupled system of 3 wave equations and an elliptic equation. So let me not mention the elliptic equation, and let me reduce the system to a scalar equation. Okay. So in other words, after having performed the previous manipulation, you get a scalar wave equation of the form D'Alembert G of phi is a sum of null forms plus lower order terms. Okay, so again, lower order terms are the cubic terms. So you have so after you reduce, you see the wave equation. You kill the spatial gradient term due to the projection of the divergence-free vector field. So the other thing you see are these quadratic terms which have the null structure, and which I call null forms, and then lower order terms. And now you want to, as this morning, run the energy estimate. Why? Simply because you would like. So at this stage, you like to control the curvature in L2, but remember that the curvature in L2 is at the level of one derivative of the connection one form. So the only thing I need to control is one derivative of the connection one form in L2, and that's exactly what's provided by the energy estimate. Okay, so here phi is a component of the connection, is one of the components of the connection one form. So if I run the energy estimate, that will control first order derivative of phi in L2, and therefore that will control the connection one form in one derivative of the connection one form in L2, and hence the curvature tensor in L2. Okay, so the only thing that remains to be done at this stage is to close the energy estimate for that equation. Okay, so what do you have to do? Well, on one hand, you have to control the energy estimate. Again, as I said, unlike this morning, because it's not the flat wave equation, there is an additional term which is dangerous in this energy estimate. So I'll discuss that at the end of the slide. And then you need to control the L2 space-time norm of these null forms. So that's why you have to prove these Baglian estimates I was talking about. Okay. So so to prove these Baglian estimates in a quasi-linear setting, here is what you have to do. So of course, here the proof is, as we'll see, has to be totally rethinked compared to the seminar case where you just rely on Fourier transform. Okay, so here on a curved background, which is rough, you can do that. So the first thing you use this basic plane wave representation I was talking before of step C. So this is what we'll focus in the last lecture tomorrow. But definitely you have this main basic building block, which is the plane wave representation. So it turns out, as I said, that it's only an approximate solution and that you need an exact representation. So out of an approximate solution, you can always build an exact solution by iterating an infinite number of times the Duhamel formula. So you write your phi as an infinite converging sequence of basic parametrices iterated by the Duhamel formula. And then once you have this, you can essentially just reduce to one term in this sequence and basically replace, if you want, phi by the representation formula in your Baglian estimates, and I'll say in the second hour, I'll show how this goes. And so we'll see how you have to rethink the proof of the Baglian estimate in the quasi-linear setting. That is, you cannot rely on Fourier transform, but rather you have to rely on this representation formula, and we'll see in the next hour how this goes. And then it turns out that these Baglian estimates are of two types. Again, exactly as this morning in Young-Mills, where you had two types of Baglian estimates, and one of them requires additionally to prove these sharp L4-Strickhartz estimates. Okay, so that's another thing you have to do. And finally, regarding the energy estimate, remember that in the energy estimate we saw, maybe I can show it again from this morning. Where is the energy estimate? Well, first of all, let me mention that again in Young-Mills we saw that there are two types of Baglian estimates you have to prove. So it's the same thing in our framework. It's analogous, if you want. And let me also show the energy estimate. The general, where is it? Sorry. So it's probably. So here you see that with respect to the flat case, in the curve setting, the additional term is this one here, because it involves the deformation tensor of T, and because now T, you don't have the symmetries in general, this deformation tensor is non-zero, and hence this term, this gives you a new term in your energy estimate. And it turns out to be also dangerous. This term is now trilinear. So what you have to do, sorry, why? No, it's here. No, yeah, no. Okay, so this term, it turns out to be trilinear. So here you have to show that this trilinear term, which is also dangerous, has also the null structure. And you have to control the corresponding, to derive a corresponding trilinear estimate. Okay, so this I won't discuss because, it will be enough to see Baglian estimates, I guess. Okay, so let me finish this hour, before the break, by showing you what is the. Okay, so anyway, so this finishes the proof, provided I tell you about the two things. Well, first of all, this finishes the proof, provided you can prove bilinear estimates and Strickhartz estimates and trilinear estimates, and provided you rely on the building block of having constructed and controlled a planar representation. Okay, so that's what we'll do in the rest. I'll talk in the second hour here. I'll talk about Strickhartz bilinear estimates, how to prove bilinear estimates and Strickhartz estimates in a quasi-linear setting, and then tomorrow we'll deal with the planar representation formula. Okay, so what I want to do before the break is present you at least explain what is this planar representation formula and why is the Econel equation important here. Okay, so this is my basic plane wave. So I'd like to have a plane wave representation formula. A plane wave representation is always a superposition of plane waves, exactly as in the flat case. And here, I'm going to consider first one basic plane wave before we take linear combinations of them. Okay, so the basic plane wave. Okay, so the basic plane wave. Let me first tell you what is the analogous in the flat case, so that you have some, so that you notice that you know this. So this is just. So in the flat case, this corresponds to EI lambda t plus, well, actually it's plus or minus t plus x dot omega. Okay, so that's what you get in Minkowski. So that's my plane wave in Minkowski. As I'll show in the next slide, with this plane wave, that's how you recover the basic plane wave representation of the wave equation. Okay, so that's what we're trying to generalize to a curved space-time. So you take a plane wave EI lambda u of tx omega. So here tx, well, I mean, it's just it's just a point in space-time. I don't mean to take coordinates here. There are no coordinates, but it's just to represent the fact that it's physical space variable. It's in the space-time. Okay, and lambda and omega are Fourier space variable, so they live in the Fourier space if you want. Okay, I mean, you should think of them as living in the Fourier space, and lambda omega is just the well, the polar decomposition of a vector in R3, right? So if I have my frequency psi in R3, I want to write it as norm of psi times psi over norm of psi. So this guy is lambda, and this guy is omega, which lives on the two sphere, and this guy is lambda, which lives on 0 plus infinity. Okay, so here psi is in R3. So psi in R3 is my Fourier variable, but instead of looking at psi in R3, I systematically decompose in lambda in omega, where lambda is strictly positive and omega is an angle on the two sphere. Okay, so that's my basic plane wave representation, and now a basic plane wave. And now I'd like to say that in some sense it's a good approximation of the wave equation, because I'm trying to get a representation formula. So let me apply the wave operator to my plane wave, and I'm going to get two terms, right? The first derivative falls on the exponential, and you get I lambda derivative of u times the exponential. And then the second derivative of my wave operator, either it falls back on the same term or it falls again on the exponential. If it falls back on the if it falls again on the exponential, you pick a second I lambda term, so you get minus lambda square, and then you get g alpha beta d alpha u d beta u. The first u is the first derivative, the second u is the second derivative you took of the exponential. So that's the first term, and the other term is the term where it falls back on the same function. So you get two derivatives on the same u. So you have I lambda, which you pick from the first derivative, and then because you have two derivatives on u, you get back the wave equation this time applied to u. And everything gets multiplied by your plane wave. Okay? So in this, you should understand that the main problem is the term in red here. Why is it a problem? Well, it's a problem simply, so first of all, I will not be able to cancel the two terms here unless there is a specific miracle which happens in flat case. You can never cancel the two, so you have to choose, you have to pick one. Choose the one which is your main enemy. So I claim that the main enemy is the one in red here because you have this lambda square, and since lambda is a frequency, this means taking two derivatives. So here in Fourier space, multiplying by lambda square is like taking two derivatives in physical space. So you're taking two derivatives of your function. Once you're taking two derivatives of your function, but the wave operator only is able to recover one derivative. So here you lose derivative in the process. So the only way to have a good representation formula which does not lose derivatives is to kill this guy. And therefore you see that it has to satisfy, you have to pick u such that g alpha beta d alpha u d beta u is 0. And therefore you have to choose u satisfying the Econal equation. Okay? So that's hence the Econal equation. That's how it appears here. So from now on, I'm picking u satisfying the Econal equation, and hence my plane wave satisfies the following equation: Dalmatian g of ei lambda u is ei box g u ei lambda u, because I killed the first term, but I still have the second term. Okay, and you see why in general it's an approximate formula, but in the particular case of the flat wave equation, it is an exact formula. In the flat case, you have a miracle, which is the fact that since my phase in the flat case is linear, when I apply the flat box of t plus x dot omega, I get 0. Okay, so that's why you get an exact formula in the flat case. Okay. Okay, but again, in general, unfortunately, it's only an approximate formula, but it will be enough for our purposes. And once now that I have this basic building block, and of course, remember that precisely in the flat case, t plus x dot omega, well, no, I don't think I said that, but okay, but you can check, indeed, you can check that t plus x dot omega does satisfy the equinal equation, right? In Minkowski spacetime. Okay. So now, let me take the last 5 minutes to actually present you the full parametrics, the one I take when I sum. So now I'm taking a linear combination of all these plane waves to be able to generate. So why do you have to take linear combination? Simply because I'm trying to approximate the following problem. I'm trying to approximate D'Alembert G of phi is equal to 0. So that's in M. And phi restricted to sigma naught is equal to phi 0. And the derivative of phi, T phi, restricted to sigma naught is equal to phi 1, where again, remember that if I have sigma 0 or even sigma t, I'm calling t the unit normal future directed to my space-like hypersurface. Okay, so sigma naught is my initial space-like hypersurface, and I'm trying to get a representation formula for this wave equation. Okay, so it's not good enough to have an approximate solution of this equation. I still need to recover the initial data. And the way you recover the initial data is by taking an infinite linear combination of these plane waves and showing that I can generate any initial data. Okay, so here is how it looks like. So here there's a sum of a plus and minus. So this plus minus corresponds in the flat case to the fact that I can take plus or minus t plus x dot omega. I get always two choices. For my equinal equation for a given initial data, I always get two choices, plus or minus. So this corresponds to decomposing the wave equation in the sum of two half waves. Or if you get to Fourier space, it corresponds to decomposing in sine and cosine, or exponential I and exponential minus I. Okay, so that's the sum of two half waves. Then I'm summing. So again, I'm taking a linear combination of all my plane waves. So this is the sum of all plane waves, all possible plane waves, which is now an integral because you have infinitely many. And this integral runs for all angles omega on the two-sphere and all lambda from 0 to plus infinity. This is my basic plane wave of the previous slide, I lambda u plus minus tx omega. And then this is the weights of my linear combination. These are coefficients of my linear combination, which obviously are functions of lambda and omega. And then you have so lambda squared d lambda d omega is simply the volume of R3 in spherical, in polar decomposition, in spherical decomposition. Okay, so that's the volume of it. That's the R squared dr d omega you're used to. Okay, so now I'd like to. So first of all, so again, u satisfy the equinal equation, and here let me talk about this dependence of u in omega. So far I did not say what is the dependence in omega. So for now, let me just talk about the asymptotic behavior. Here, this parameter omega. I mean, this should be seen as the equinal equation depending on an extra parameter omega. So my equinal equation depends on extra parameter omega, which prescribes the asymptotic behavior at space-like infinity. So as x goes to plus infinity on the initial slice. Okay, so here, the way you prescribe this is, of course, it's influenced by the flat case, and it is to be able to generate any initial data. Okay, so to generate any initial data, I need to properly pick this f plus minus, but I also need to, I need also to ensure this to make sure that I have a correct, that my phase oscillates enough in omega. Okay, so here, actually, this phase, this x dot omega is simply, you can see in the flat case, you can see that what you get back is the phase of the inverse Fourier transform, which is an isometry on L2. So that's the point. Okay, so here let me tell you what is the analog in the flat space. Okay, so you will realize that you actually know this parametric. So you know it for two reasons. First of all, you know it from the flat case because in the flat case it's totally explicit, right? Again, in the flat case, so if Mg is the Minkowski spacetime, you recover u plus minus of tx omega. Again, it's minus, it's plus minus t plus x dot omega. And you can actually identify f plus minus of lambda omega is equal to 1/2 of phi 0 hat of lambda omega minus plus I over lambda phi 1 hat. So hat, of course, is the usual Fourier transform on R3. Okay, so in other words, you get back the explicit plane wave representation formula of the flat case. This is exactly the phase of the plane wave representation of in the flat case, and this is exactly the f plus minus are simply the Fourier transform. I mean, a linear combination of the Fourier transform of phi naught and phi 1. Okay, so it's the usual formula, the plane wave, the one that you know, the one that you obtain if you take Fourier transform in space variables and you integrate the ODE. That's what you will get. Okay, and then you also know this in the curve case simply because this is what is called the so-called lax parametrics of geometric optics, or rather, I should say, this is the basic building block of the lax parametrics. Then, I mean, here this is a Fourier integral operator with a phase which satisfies the Econal equation. The lax parametrics also adds a symbol which satisfies an infinite set of transport equations, but on our rough background, we don't have enough regularity to make sense of it. So the only thing we keep from the lax parametrics is the most basic term, which is the phase satisfying the Econal equation. Okay, and those ought to be enough for all purposes. Okay. Yeah, maybe we can stop here and I'll continue this slide after. So let me finish with this slide. So okay, so I presented what is the plane wave representation we're going to use, and now I want to tell you what I mean by constructing it and controlling it. I said I have to construct and control. So first, let me talk about the construction step. The construction step is I wanted to make actually one remark that I forgot to mention. You can see in particular that here in the flat case, because at initial time you get the inverse Fourier transform, that's why actually you are able to relate your initial data in a trivial way to the Fourier transform of your initial data for the wave, f plus minus to the initial data for the wave equation. Okay, so I forgot to mention that. Okay, so what I call the construction is precisely that I am able to do, as in the flat case, I'm able to generate all initial data for the wave equation. That is, for any initial data, phi 0, phi 1 for the wave equation, there do exist f plus minus such that the parametrics at initial time is given by phi naught, and the time derivative of the parametrics at initial data is given by phi 1. And furthermore, that's not enough. I also need, of course, I need estimates. So I need to say that not only do there exist f plus minus, but I do control this f plus minus in the sense that lambda times f plus minus in L2 is controlled by a gradient of phi naught in L2 and phi 1 in L2. Okay, so that's the sharp estimate. That's the estimate that's true in the flat case. And in particular, if you take my formula here relating f plus minus to phi 0 hat and phi 1 hat, you can check using Plancherel that this inequality here is actually inequality in the flat case. Okay, and I can also prove that I have equality, but it's this inequality that's going to be useful to us. Okay, so that's the construction step. The construction step is essentially, as you can see, inverting a Fourier integral operator, because I have a Fourier integral operator applied to f plus and f minus, which is equal to phi 0 and phi 1. So I want to invert this Fourier integral operator, and I want to say that the inverse is bounded, essentially. Okay, so that's the step. And then you have the step about the control. So what I mean by a control of the parametrics of this approximate solution. So first of all, recall that this parametrics is not an exact solution, right? As we have said, if I apply D'Alembert G to my representation formula, I don't get 0. Remember from the previous slide, you don't get 0, you get this term here, which comes from the fact that you're not in the flat case. So instead of getting 0, you get this I D'Alembert G u plus minus, and here, because you had lambda square and you pick up an additional power of lambda, you get a lambda cube here. In other words, D'Alembert G of my parametrics gives you an error term, which is a Fourier integral operator with, again, the phase u. And now you have the symbol D'Alembert G of u plus minus, which, again, is 0 in the flat case. Okay, so in the flat case, it's an exact solution. But in the curve case, because this is not 0 in general, you get this error term here. And we'll see actually tomorrow when we look at the Econal equation, we'll give a geometric interpretation of this term here in connection with the Econal equation, with the level sets of the solution of the Econal equation. But for now, let me just keep this notation. It's going to be enough for now. Sorry? So plus minus is the fact that you have two halfways. So it corresponds to the fact that in the flat case, you have plus minus t plus x dot omega, right? It's always, so these functions are always functions of t, x, and omega. I mean, if you want space-time variables and the parameter omega, but there are two of them, right? I'm summing of a plus and minus. So in other words, you have a first integral with u plus and a second integral with u minus. So f plus minus, precisely, a priori it's unknown, but you do show that there is no formula. I showed the formula, right? I showed the formula in the flat case here, but in the curved case, you do show that there exists f plus minus. We will show that there exists f minus, which generates the initial data and satisfy this estimate. Okay. Okay. So you have this error. So you generate this error term here, and so what? So now I want to explain what I call the control of the parametrics, control of the approximation formula. So your approximate formula does not satisfy the wave equation, but it does satisfy this approximate wave equation. So Dalmatian GS is equal to E, and phi on sigma naught is, S on sigma naught is phi. S on sigma naught is phi 0, and TS on sigma naught is phi 1. So if I want to run, so controlling S via the energy estimate, provided I know how to close it, that's equivalent to controlling the L2 space-time norm of the right-hand side here. So in other words, to control the parametrics, essentially the only thing I have to do in principle is just to control the L2 space-time norm of the error term, which is the derivation G of S. And here, what I'm asking is to get the sharp control of this error term. In other words, even in this curved and rough setting, I still want to get the estimate, which is the correct one. That is, what I mean with this is that if u plus minus was the one of the flat case minus plus t plus x dot omega, and if this was a smooth symbol, or even 1, then this is the estimate I would see. So I want to get the same estimate as the one which is sharp in flat case. Okay? Okay, so that's again. I mean, this business about the construction and control of the parametrics. This is what we'll see in tomorrow's afternoon lecture, in the last lecture. But for now, what I'd like to focus on is explain you how, in this rough setting, using this plane wave representation, you can prove Bayesian estimates and Strickard's estimates. Okay, so let me first state what are these Bayesian estimates. So I take, again, I'm going, from now on, most of the time, I'll just keep one plane wave and not two, because the proof is the same for each plane wave, so it doesn't really matter. The sum of the plane waves is needed to generate all initial data, but now, from now on, I can focus on one of them. So let me drop the plus minus index. So let me recall you that this is our plane wave representation. And now I'd like to prove Bayesian estimates. So what are Bayesian estimates? So here are the two statements of Bayesian estimates that I want to prove. So again, our null form is this one. So Qij phi psi is di phi dj psi minus dj phi di psi. And I'd like to control Qij of phi f psi in L2 space-time. I'd like to control it by, so again, so you have to imagine these null form in principle that are applied to two solutions of the wave equation. And now, because I have this plane wave representation, I am replacing one solution of the wave equation by its plane wave representation. And then I want to control this by the L2 norm, the L2 norm in R3 of lambda square f times the sup over any null hypersurface of derivative of psi in L2 of the hypersurface, where here, again, H is any null hypersurface, and this derivative here denotes all the tangent derivative to null hypersurface. So let me remind you that when I have a null hypersurface, I have 3 tangent directions. One is the generator of the hyper. So if this is my hypersurface, so I have L, and then I decompose also, I have E1, E2 here, and the tangential derivative, so this means either L psi or tangential gradient of psi. Okay? Okay, so why is this good enough? So I want to check, okay, so let me convince you that this is the equivalent of the first estimate of Yang-Mills we saw this morning. So the first estimate this morning was the following. So if you want, the first null form this morning was equivalent to the following. So you have, yeah, okay, well, let me do it here. Yeah. Yeah, okay. No, let me do it here. Okay, so then we had the following estimate. One of the null form this morning was the L2 norm of Qij of d minus 1a a L2 of R1 plus 3, and you'd like to control this by the initial data in H1. Let's say 0 in H1 plus, H0 in H1 square plus A1 in L2 square. Okay? So that's, if you remember, that's the first null form of Yang-Mills. And I claim that this first null form of Yang-Mills is the exact equivalent of this one here, simply because, first of all, you can see that if I write it with phi and psi, so let me, if I call this, sorry, that's phi. So if I call this to be phi and this to be psi, then you see that phi is actually in H2 and psi is in H1. Okay, because H2 because of the gradient inverse here. Okay, so here this phi is in H2, so I should expect to control it by the H2 norm. But of course, here, remember, lambda is a frequency parameter. So 2 derivative of phi in L2 is equivalent to lambda square f in L2. Okay? Because for each derivative, I pick a power of lambda. Okay? And then, why is this the equivalent of the H1 norm? Well, remember, this morning we talked about the characteristic energy estimate, and we said that when you run the energy estimate, you get not only, you cannot get, of course, information on a space-like hypersurface, but you can also get information of a null hypersurface. And remember, if you use null hypersurfaces, the only information you can recover is not all derivatives, but only the tangential ones. Okay, so let me mention at this step already that, of course, what will be important in the null form here is the fact that I do recover only tangential derivatives here. If I did not have a null form, I would see all derivatives here, and therefore this would be useless because I could not control it from the characteristic energy estimate. Okay, so that's where the null form, that's where the structure of the null form is going to be crucial. Okay, so that's for the first null form. Now the second null form I claim is also analogous to the one of Yang-Mills. So here, by the way, at this stage I should mention that remember there were a whole host of null forms coming from first the Yang-Mills formalism, but also commutation with scalarization and projection divergence free vector fields. But it turns out that if you work, you can essentially classify them in 2 families where the main estimates are these ones precisely. Okay, so that's the second one. So let me remind you that for the second estimate in Yang-Mills, the null form that you have is the following. You have d minus 1 q. So the difference between the two is that the d minus 1 is either inside or outside in Yang-Mills. So you have also d minus 1 qij a. So of course it's a system, so this is not a trivial expression here. L2 space-time, again, is controlled by a0 h1 square plus a1 L2 square. Okay, so here, that means I'm taking an inverse derivative of q of a with a in h1. So you see that this is exactly what you have. You take an inverse derivative, you have qij of, so here I'm replacing actually both functions by their plane wave representation. So I have gradient minus 1 of qij, first function phi corresponding to phi 1, phi corresponding to F2, sorry, phi corresponding to F1, and phi corresponding to F2, L2 in space-time. And then here, you see the equivalent of the H1 norm, which is that lambda, because lambda is a frequency parameter, I get 1 power of lambda times F1 in L2, and 1 power of lambda times F1 in L2, and 1 power of lambda times F2 in L2. Okay? So that's the exact analog, again, of the second generation of Bayesian estimates for Yang-Mills. Okay? Okay, so here, actually, again, the structure of the null form will be crucial, but here we'll see in the proof because I can't just explain it on the statement. But it will be actually, the interesting thing is that the null structure will be used in a very different way for both estimates. Well, we'll see later. Okay, so now let me, let me prove these estimates. Okay, so the first type of Bayesian estimates is actually the first proof is very simple. So what you do is the following. So remember, you want to estimate this expression here. Well, okay, so let me just refresh your memory and actually mine at the same time. So I'm trying to estimate the L2 norm spacetime of Qij phi f psi by lambda square f in L2 and the sup over any null hypersurface of only tangential derivative of psi in L2. Okay, so I'm trying to estimate this quantity here. So Qij phi f psi, I can, of course, move the derivative of the Qij form under the integral, in which case you get the following. So first you have Qij of exponential I lambda u times psi, and then when the derivative falls on the exponential, you pick a power of I and the exponential here, and you simply get Qij u psi times f of lambda omega lambda cube d lambda d omega. Because you have differentiated the exponential, of course you have an extra power of lambda here. So you go from lambda square to lambda cube. Okay? Now I want to estimate this oscillatory integral in L2 space-time. So the first thing I want to check is what is this expression here, and that's where the null structure is fundamental. Okay, so you look at Qij of u psi. This is diu dj psi minus dju di psi. And you can very easily check that this corresponds to a tangential derivative of psi if I consider as a null hypersurface the level sets of u. Okay, so we will see, it's very easy to see, but we'll see in tomorrow morning's lecture that the solution, the level hypersurfaces, the level sets HU of solution of the econal equation are null hypersurfaces. Okay? So we'll see that tomorrow morning. It's a very easy computation, but we'll see that tomorrow morning. So, but for now, assume that because U is solution of the econal equation, automatically the level hypersurfaces of U are null hypersurfaces. And because you have this curl structure, if you want, automatically the derivative of psi is orthogonal to the derivative of U, and hence it's tangential to the level surfaces. So therefore, you only get tangential derivative. Okay? Okay, so that's the only place where I use the null structure is by making this observation here. Okay, once this is done, then the rest would go through for any form, not only a null form. So now I can take now I want to take the L2 norm spacetime of this expression, and the first thing I'm going to do is something which a priori is terrible, as the fact that I'm totally ignoring the oscillations in omega. I mean, remember this is a phase which in the flat case is minus t plus 6 dot omega. So you have oscillations in omega, but here I'm putting the L2 norm inside, and I'm putting the omega integral outside of the norm, which means that I'm totally ignoring the oscillations in omega, and I'm just keeping the oscillations in lambda, but it turns out to be enough. And then see that what you get are two types of terms. First, you have this Qij of u psi, which is independent of lambda, and then I get this integral over lambda. And now I want to decompose this L2 norm by using, if you want, I want to do the following decomposition of my L2 norm. I want to say the following. I want to say that I want to break my product. So I have, let's say, if I have H1 times H2, L2 of M, I want to say that this is less than H1 L infinity with respect to U L2 in HU times H2 which is L2 in U, L infinity in HU. Okay, so in other words, I have a foliation of my space-time by level of hypersurfaces of U, and I'm taking as variables the U variable, which is orthogonal to the level foliation of the level hypersurfaces, and the variable tangential to the hypersurface. Okay, so I'm decomposing my L2 of space-time like this. And furthermore, notice, so one of the terms is this one, that's the first term, L infinity U, L2 in HU. And the other term, well, it's L2 in U, L infinity HU, but of course the fundamental observation is that it only depends on space-time variables through the U here, and therefore the U is orthogonal to the variables in HU. Okay, so therefore I can drop the L infinity in HU, which of course would be terrible for me, because it actually only depends on U. Okay? Okay, now that I did this, there are two things I can do. First of all, this guy, I want to take the soup also in omega to put it outside of the integral. So I get the soup over omega and U of Qij U psi L2 of HU. And then this one here, notice that now with respect to U, this is just the one-dimensional inverse Fourier transform. So now I can use the usual Plancherel here. So I can use the usual Plancherel because I have L2 of U. This is the Fourier transform. U is the Fourier variable for the one-dimensional inverse Fourier transform. So by using Plancherel, this you simply get L3F of lambda omega, L2 L omega. Okay, this is just Plancherel. Okay, and finally, so remember now the formula for Qij. So Qij is just a tangential derivative of psi. So this is just the L2 norm of a tangential derivative of psi, where you take the soup over all omega U of L2 of HU, but these are, in particular, special example of null hypersurfaces. So I can even take the soup over all possible hypersurfaces here, times L2 over the hypersurface. And remember that I only got tangential derivatives, so that's the crucial part. Now the null structure is there. The null structure is the fact that you only keep tangential derivative. And then here, if you count the number of powers of, so you have L2 in lambda. So if I square this, I would see lambda 6 times f square, and then I can do Cauchy-Schwarz in omega. So then I would have lambda 6 times f square. So lambda square is used for the volume in R3, and then I'm left with lambda 4. So if I take the square root, I'm left with lambda 2 f L2 of R3. Okay, well, I mean, it's straightforward computation in counting the powers of lambda. Though of course, you have to remember there are lambda square in the volume of the element in R3 decomposed in spherical coordinates. Okay, and that's how you get actually the estimate that I was mentioning in the previous slide. You see that you get this term and this term indeed. Okay, so that's for the first Bayesian estimate. Now let me show you another way you can use the null structure. And it's always like this for null structure. You have always two ways to use the null structure, just by looking at what are the directions of your derivatives. The other way is to integrate by parts. Okay, so let me show you the other way, and so you will have, if you never saw it, you'll see the two applications of the null structure. Okay, so now let me maybe remind you what is the second estimate. So the second estimate is this one. I want to take inverse gradient of my null form applied to two representation formula, and I want to argue that it's controlled by lambda f1 in L2 and lambda f2 in L2. Okay, so again, let me start. So let me remind you what. So first of all, the first thing I do is I start decomposing in frequency. Okay, so I have my representation formula, and I want to write my representation formula in sum of representation formula decomposed in d-adic shells of size. I mean, it's the usual thing, right? So you take a partition of unity, you decompose in d-adic shell of size 2 to the p. So here lambda is of size 2 to the p for phi fp. Okay, so I decompose in frequency in the usual way. That's the so-called first d-adic decomposition of harmonic analysis. At least that's how it's called in the book of Stein. Okay, so you take Qij of phi and psi, and now the fundamental observation you want to make here is that you can integrate by parts, but more to the point, you can choose how you integrate by part. So here, I can either say that this is di phi dj psi minus dj phi di psi, or I can say that it's dj psi di phi minus di psi dj phi. Okay, you can rewrite a null form in these two forms. And the important thing is that because you have these two, if you want these two, these are integration by parts, right? So because I can do, you see what's magical about this integration by part is that I can choose which of the two functions phi or psi receives the most derivative. Either I choose phi to have zero derivative and psi to have one derivative, or I choose psi to have zero derivative and phi to have one derivative. Okay? So why is this important? Well, what you do is the following. I'm starting with the null form which I want to estimate, and I start decomposing in frequency. So I'm summing over all possible Laplacian minus 1 Qij of phi f1p, phi f2q. So I'm summing over all frequencies. And of course, I can always assume that one frequency, that p, for instance, is larger than q. So now what I do is, since q is the lowest frequency and p is the highest frequency, the goal is always to put less derivative on the highest frequency. And this integration by parts allows me to do this because I can now choose that I can choose to see this null form as a derivative of phi f1p df phi f2p. So in other words, I put more derivative on the lowest frequency. Okay? So again, that's the only thing I use. That's the only place where I use the structure of the null form, the magical structure. From now on, it's a general estimate. Okay? So now I have Laplacian inverse, gradient inverse of a derivative. So this is bounded on L2. So I can remove this. And I'm left with the product of phi f1p d phi f2p. F2q, right? So now I just break the product in L4 and L4. It's very easy. So I put this guy in L4, this guy in L4. And that's where I need my L4 Strickhartz estimate. Okay, that's where I'm going to use my L4 Strickhartz estimate. So here, recall the L4 Strickhartz estimate. Well, okay, I did not say what it was, but in the flat case, so recall. So what you have is that you have phi f decomposed so how did I write it? Phi fp, right? Phi f decomposed in frequency p in L4 of m. So the L4 Strickhartz estimates. Remember that in the flat case, it's connected to the h1 half norm of the initial data. So here, because I'm localized in frequency, what is the h1 half norm? That's lambda 1/2 of f in L2 of R3. Okay, that's the Strickhartz. So that's the Strickhartz estimate we'll have to prove in starting with the next slide. That's exactly the Strickhartz estimate we will prove. So sorry, yeah, I should actually. I don't even need a frequency. I can just put it like this. Okay, so the Strickhartz estimate in the flat case at least tells you that the L4 norm spacetime of your solution of the wave equation is connected to the h1 half norm, and because here lambda is my frequency parameter, h1 half means that I multiply by lambda 1/2. Okay, so that's the exact analog of the Strickhartz estimate, L4 Strickhartz estimate in dimension 3, and that's actually the estimate we're going to prove in the next slide. Okay, so here, okay, well, sorry, where am I? Okay, so I'm here. Okay, so now I want to use this Strickhartz estimate. So this Strickhartz estimate, you can see it loses half a derivative here, or half a power of lambda, half a power of lambda here. So if you go back to 1 power of lambda in each of these guys, you see that you have the correct number of powers of lambda, except that you lose 1/2 of the highest frequency and you gain 1/2 of the lowest frequency. Okay, because you lose 1/2 of the lowest frequency and you gain 1/2 of the highest frequency, you get this extra factor here, which is crucial because this is what's going to give you summability. Because now I need to resum in all p q's, but now because I had this, well, I guess I don't know. I mean, it's you can do Cotlar-Stein. I mean, you get this now. You can sum. You can use this to get summability, and once you sum all these pieces in L2, you recover the full L2 norm of lambda f1 and lambda f2. Okay, so the interesting thing here is that, so what is it that you do compared to Strickhartz, for instance? Strickhartz would be to do the same, where instead of putting L4, L4, I put L2, L infinity, and L infinity, L2. And that one does not work. So the idea is how here you use the null structure to exchange the bad Strickhartz, which is the endpoint, which is not true, by the good Strickhartz, which is L4, L4. Now you play with the derivatives, you use this integration by parts to reduce to a Strickhartz which is correct, which is the L4, L4. Okay, so that's the main idea here. Okay, so now let me finish this lecture. Now let me focus. So this was it for binary estimates, and now I'd like to talk about the other ingredients here which we use, which is this L4 Strickhardt estimate. Okay, so I'd like to explain a little bit. So how much? Yeah, that's fine. I'd like to explain how you recover sharp Strickhardt estimates when you have a very rough background. Okay, so I want to recover the same Strickhardt estimate as the one which is correct in dimension 3 for the flat wave equation, the one I showed this morning. And again, at this stage, so first of all, I remind you our representation formula. So you have this integral of S2 and 0 plus infinity of EI lambda U. So again, I'm dropping the U plus minus because you can do the same for each half wave. So it's just U of Tx omega, and then I'm adding here an extra frequency truncation psi 2 minus j lambda, which localizes lambda of size 2 to the j, exactly as in the previous slide. So it's your frequency cutoff, with psi is localized, for instance, between 1/2 and 2. F lambda omega, lambda squared d lambda d omega. Okay, so the same parametrics, except that now it's localized in frequency as in previous slide. So here, it turns out, as you saw from the previous slide, the only thing I have to prove is a Strickhardt estimate for these parametrics localized in frequency. Now, if you're used to Strickhardt estimate, you know that anyway that's the hard part. Okay, when you prove Strickhardt estimate in the flat case, you start localizing in frequency in the same way here, and the fact that and you easily reduce to proving Strickhardt estimate for the localized representation by standard little loop Paglia analysis. Okay, so anyway, it's not like I'm cheating here. Proving Strickhardt estimates for this is anyway the hard part that you have to prove. Okay, so here is the result. So first of all, remember we have to prove an L4 Strickhardt estimates, but in the end, well, for quite some time we thought that would be easier to prove L4, but it turns out that it's actually not more difficult to prove all Strickhardt pairs. So in the end, I obtained a result for all Strickhardt pairs. So remember the Strickhardt pairs are PQ such that PQ are larger or equal to 2. Again, Q strictly less than plus infinity because the endpoint is not allowed in dimension 3. And then they satisfy 1 over P plus 1 over Q is less or equal to 1 over 2. R is 3/2 minus 1 over P minus 3 over Q. And then the statement is that under assumptions on the phase, which I'm going to give in the next slide, which are compatible with L2 bonds on the curvature, the parametrics localized at frequency J satisfies the following Strickhardt estimates, phi J LP. So here I'm only proving local in time Strickhardt estimates, which is the only thing I'm needing. So it's LP in time, LQ in space, and it's controlled by 2JR psi 2 minus J lambda F in L2 of R3. Okay, so here, so again, these assumptions on the phase compatible with L2 bonds on curvature, it means that I'm going to make assumptions on the phase which I am able to recover by only assuming L2 bonds on curvature. In other words, if I look at the econal equation on the spacetime with curvature bounded in L2, I will make assumptions which I'm able to prove. Okay, so I'm going to do this in the next slide. Let me also mention that, of course, in this setting, the L4 Strickhardt estimate corresponds to P is equal to Q is equal to 4, and therefore that corresponds to R is equal to 1/2. Which means this is why you get the power 1 lambda to the 1/2 in the previous slide. Okay, so that's what you want to prove. So let me now talk about these assumptions on the phase I want to make to prove this Strickhardt estimate. Okay, so let me introduce a notation. I want to introduce, so here, again, this is the covariant gradient on sigma t, and I want to introduce the so-called lapse or inverse foliation density. So this, if you want this B here, which is one of the norm of the gradient of U, measures the infinitesimal distance between two level surfaces of U. Okay, so if I give you, so you have a foliation of the. Okay, so you have a foliation of, yeah, well, let me remove that as well. So for instance, if I look in sigma t, because this is expressed in sigma t, so let me just project what I have in sigma t. So in sigma t, I have a foliation of sigma t by my level hypersurfaces of U. So this is U is equal to constant. So let's say this is U is equal to U1, U is equal to U2, U is equal to U3. Okay? So I'm foliating sigma t. So in particular, remember that in the flat case, these are minus t plus x dot omega is constant. So these are planes in sigma t which are parallel to each other and orthogonal to omega. And here, B measures, if you want, B measures the infinitesimal distance between two slices, while N, which is gradient U divided by its norm, is just the unit normal, so it's the unit normal to the level surfaces. So that's N. It's the unit normal inside sigma t. Okay? Okay, and again, of course, in the flat case, I have U is minus t plus x dot omega, and you immediately see that in Minkowski, this implies that B is equal to 1, and the unit normal N is exactly omega. Okay? Okay, so I'm going to do the following assumptions on my on my phase. So I'm going to assume that B minus 1. So there is a small parameter epsilon here. Yeah, let me just say that this is connected. The fact that you have a small parameter is connected with the fact that to prove local existence, so for hyperbolic problem, you can always reduce a small local existence for a small time by a rescaling and truncation argument. You can always reduce to existence for small data on time of size 1. Okay, so this is how you. I mean, it's a usual trick which is very useful to reduce yourself to small data. So it's the fact that because you're looking for a very small time of existence, you can always rescale things so that the time is 1 and the initial data is small. Okay, so this smallness corresponds to the smallness of initial data here. I mean, it's a usual trick in hyperbolic problems. Okay, so anyway, so you have B minus 1 in L infinity plus d omega B. And remember, U depends on omega, so d omega B in L infinity is controlled by epsilon. N at the angle omega minus N at the angle omega prime is like omega minus omega prime 1 plus O of epsilon. And then I need one global feature of my sigma t, which is the fact that for all times between 0 and 1, which is why I try to control my solution, and for all angles omega in S2, U of Tx omega, d omega U of Tx omega is a global coordinate system on sigma t. Okay, so first let me make the connection with the flat case. So let me remark that the flat case, in view of the values in the flat case, all these assumptions are correct with epsilon is equal to 0. In the flat case, B is equal to 1, and d omega B is 0, so this is indeed equal to 0. And in the flat case, N is equal to omega, so this is exactly equal to this without the O of epsilon. Okay, so this is exactly exact. This is the exact in the flat case. Okay, and then for the coordinate system, it's also correct because you can see that. So what is this coordinate system in the flat case? This coordinate system in the flat case is simply the decomposition of any vector in R3. So if I take x in R3, then I can decompose x as x dot omega times omega plus d over d omega of x dot omega. So you see that this corresponds to u, and this corresponds to du over d omega. Okay, so it's just, if you want, it's just the decomposition along omega and orthogonal to omega. Okay, and it turns out that to get the component orthogonal to omega, you just need to take t over d omega. Okay. Well, we have the minus t, but let's forget about the minus t. Anyway, okay, so this coordinate system simply corresponds in the flat case to the decomposition parallel to omega and orthogonal to omega. Okay, and here, so here, let me mention, of course, again, the main constraint here is regularity. So let me mention in terms of regularity where we stand. So here you see that the assumptions we make are regular. So B is at the level of gradient of U. So we're assuming that at least some part of the gradient of U are in L infinity. And here you have also d omega B, and here essentially d omega n. So you're also assuming that one space derivative of d omega U is in L infinity. Okay, so the assumptions are making, I mean, essentially they are at the level of these quantities here. So the maximal regularity we're asking for the phase is one space derivative of d omega U in L infinity. Okay, and well, we'll see we'll see tomorrow that this is exactly what we're able to recover for the Econel equation. At least if I'm only assuming, if I want only to talk about L infinity regularity, that's the best I can get. That's actually optimal. I cannot get any bit of, I cannot get more information than that if I'm measuring regularity in L infinity. And let me also compare this with the classical method for proving Strickhart's estimate. So the classical method, so you have a representation formula which is an oscillatory integral, and I'll go back. I'll discuss again the classical method later on, but let me first say that in the classical method for proving Strickhart's estimates is the stationary phase method. And the stationary phase method does require, there is a special change of variable in the stationary phase method, and this change of variable requires one derivative. Actually, it's one time derivative. Well, okay, I'll be more specific. It's a one-time derivative. So it's one-time derivative, or at least it's one space-time derivative, and two omega derivative of u in L infinity. Okay, so if you want the usual method, the standard method, which is based on stationary phase, uses at the least this amount of regularity. That's just to make sense of the change of coordinate. Of course, after that, you still have to integrate by parts. So really, this is the minimum. As soon as you start with the usual standard method, this is what you would need. Okay. So here we do need to beat the standard method, but quite a bit simply because here we have one more derivative than what is the minimum required for that method. Okay. So you have to proceed quite differently. Okay. So now let me show you a bit how this goes. So you use the so-called. So the first part of the proof is the standard one. It's the so-called TT star method, which is extremely standard and used in all sorts of. And the TT star method is whatever you do when you have an oscillatory integral. It's always you want to use to exploit the oscillations. You always multiply. So I always get confused. So you multiply on the left or on the right by the adjoint of the operator, which corresponds to integrity by parts either in X or in omega, according if it's on the left or on the right. So here I think I do use TT star. Okay, but so anyway, you take your plane wave. Sorry, so you go here. You take your plane wave. TT star is I take this plane wave representation and I multiply on the right by its adjoint, and I look at the kernel of the corresponding operator. That's the TT star method. Okay, and it turns out that the kernel after rescaling. So you do a rescaling procedure. Because you have this, remember you have this 2 to the j here. So you after some rescaling, this is what you see. This is the kernel of the TT star operator after rescaling. So you still see, your phase ei lambda, but now you have, because of the rescaling, you have 2 to the j phi t over 2j x over 2j s over 2j y over 2j omega. Where because I did TT star, I don't get one phase, but instead I get two phases, right? If you get TT star, you have one phase with a plus for the operator, and then because you take the adjoint with the I, that gives you a minus. So the second phase comes with a minus sign. So you have UTX omega minus US EY omega. Okay, so the standard TT star procedure. And then, of course, you have your cutoff, and because you have a cutoff square, because one comes from the adjoint and the other one from the original operator. So you have psi of lambda square d lambda d omega. Okay, so far, it's the standard proof, and in particular, the standard TT star estimate after rescaling. You can reduce everything to the following dispersive estimate. You want to prove that your kernel, want to prove that the oscillation of the phase are such that your kernel decays like 1 over t minus s. So that's the estimate you want to prove. That's the so-called dispersive estimate. Once you have proved this estimate, then you can conclude, as usual. If you're aware of the standard method, you conclude by interpolation and using the Hardy-Littlewood inequality. Okay, so and you prove the Strickhardt. Okay, the only thing I want to mention is that this is very standard, and the only contribution here is how you get this estimate. And the only difficulty, in the standard method, everything goes through except that you have to prove this estimate with a phase which has very little regularity. Okay, so that's what I want to do. I want to take this kernel and convince you that we can prove this estimate with lower regularity than the usual method would pretend you need. Okay, so this is the first time that we depart from the standard method. That's where we integrate by part in lambda. So here, I want to exploit the fact. So if you want, in the standard method, you rather integrate by part in omega, or at least you change variables in omega. I don't want to touch omega because you see there is a dissymmetry in my phase. I have very little regularity in omega. I cannot take more than one derivative in omega. However, as seen in the assumptions, however, of course, lambda, because I have a phase which is homogeneous of order 1, I am smooth with respect to the lambda parameter. So lambda, I can do what I want. I can integrate by part infinitely many times if I like it. And therefore, I want to exploit this. So what I'll do is that first, I use this observation to integrate by parts twice in lambda. And I take the fact that K is controlled by, if I integrate by part twice, obviously I will get this on the denominator. So I get this 1 plus 2 at the power 2j phi square. And also I can remove the integral of lambda in lambda because this does not depend on lambda. And remember, my cutoff psi of lambda is supported between 1/2 and 2. So this allows me to bound the integral of lambda, and I just keep the integral in omega. Okay? And now, with this, you see that to obtain this upper bound for k, it means obtaining a suitable lower bound for phi. And let me, just for the sake of having something in mind, let me write exactly what kind of, let me write one example. Let me write one example of a lower bound that you would like to see. So one example. So it's actually going to depend. It's actually going to depend. There will be several regions to consider, as we will see. But basically, the estimate you would like to see, one of the estimates you would like to see goes as follows. So again, that's one example. There are other type of estimates, but I think the most basic one you should have in mind is that basically, in some sense, you would like to see this lower bound here. And in particular, you see that this lower bound. You see in particular this lower bound. If you get this lower bound, then this expression here does not depend anymore on j because you have 2 to the 2j here, and since you have a square, you will get t minus s square. So the t over 2j, x over 2j, s over 2j, y over 2j, they will the 1 over 2j square will cancel this 2 to the j here, 2 to the 2j. Okay, so here, if you get an estimate of that type, then you remove the j dependence in your estimate. Okay, because obviously I want to get something independent of j here, so it's important to remove the j. Okay. So in other words, if you believe in that estimate, which as I said, because you have other type of estimate to prove, but essentially if you believe in that estimate, then you can even forget about the 1 over 2j and just prove it for tx, any tx s y, and will be as good. Okay, so you want to derive a lower bound on phi. Okay, so now let me compare with the stationary method and explain a little bit why we do gain here. So what you do in the stationary phase is the following. You write your phase, you look at the points where your phase is stationary, which means, so the points where your phase is stationary, let me remind you, it means that you look at the points where d omega phi at omega is equal to omega 0 is equal to 0, because that's the main contribution of your, in the stationary phase method, that's the main contributions. Outside of this, you get, it's better behaved, right? So you look at the points where the phase is stationary, and you do essentially a Taylor expansion. So you see that here this is the Hessian of phi in omega. So you get the Hessian of phi at omega minus omega naught, omega minus omega naught. So this is the Hessian of phi at omega naught. And then because the Hessian is degenerate when s is equal to t, you actually have to take an additional t derivative, and you get this extra s minus t term here. And then you have little o of this. And you see that, indeed, to make sense of this, to do the Taylor expansion, it seems that you need at the least to take one time derivative and 2 omega derivatives. So you need one space-time derivative and 2 omega derivative in L infinity. And recall again that we have only one derivative in space-time and one derivative in omega, in L infinity. Okay, so why are we able to improve on this? Well, what we want to do is the following. Instead of doing this change of variable, I don't want to do it. I want to integrate by parts in omega. Remember, we integrate by part twice. And then we're looking for a lower bound for phi, which is well, let's say it's this one, right? Let's say that this is the lower bound we're looking for. Okay, so now the point is, of course, if I take this change of variable, you immediately see that you get this lower bound. But the point is that getting this lower bound, I claim, is much cheaper than getting this equality. In other words, it's easier to get the inequality than the equality. Okay, and that's where you're going to gain. Okay, and here I should also mention that this method for obtaining lower bound for phi is inspired by the overlap estimate for wave packet derived by Smith and Tataru in the context of their of the same result, but in H2 plus in their result in H2 plus epsilon. Okay, so it's a different kind of parametrics. It's called wave packet. So here you have to bound the number of wave packets through a point rather than getting a lower bound for the phase. But it turns out to be very related. The difference here is that we do it with slightly less regularity and also without having a basic coordinate system, if you want. But in essence, it's very related. Okay. Okay, so now let me tell you how you. Let me finish by telling you how you actually proceed. So you're going to decompose your space-time in 3 regions. Okay, so let me, maybe I want to start by, yeah, well, let me keep this, but let me write down the 3 regions. Okay, so I want to get this lower bound on phi, which is still on the blackboard, and for this, I want to decompose. So I'm going to start, so I can always assume, of course, that T, so I have T and S, I can always assume that T is less than S. So I'm going to write, see here, I'm going to put the point Tx. That's the point Tx in my space-time. And now I want to draw the forward light cone from Tx. And I want to consider the intersection, the section of this light cone with sigma S. And I want to, and now I'm going to look at where my point Sy sits compared to the section of the light cone, which I'm going to call S, right? Okay. So there are essentially 3 cases. Well, I mean, it's easy. You're either inside, outside, or on the light cone, right? So either you are inside, so Sy could be here, or it could be here, or it could be here. And the proof is actually different for each of these cases. Okay, so for that, you introduce this function Sz, which is the max for all omega running on the 2-sphere of u S z omega minus ut x omega. And you actually identify S. So here, S, I should say, you know, I'm drawing the picture essentially in flat case. So I'm making as if these objects were very nice here. I'm in a rough setting. I have no idea what this cone looks like. And the good thing is that it's a very robust method. I actually don't care how this cone looks like. In particular, the only information I want is that this cone S is just a congruence of geodesics. Actually, I'm looking at the future directed null geodesics issued from that point. I don't care that they span a nice manifold. It's just a congruence of geodesics. In other words, I just need a C0 manifold, so something very weak. That's the only thing I'm needing. And here, actually, the only thing I need actually is that I can realize the intersection of the forward light cone with as the zeros of the function f, which is a continuous function. Okay, so I just want to say that this congruence on geodesic corresponds to 0 of a continuous function. That's the only thing you need. Okay, and now, and actually you can see that this m here corresponds to it actually measures essentially, at least in a flat case, it measures the distance from the point to the light cone. So of course, if it's on the cone, it's 0, and then if you're outside of the cone, either inside or outside, m measures the distance of the cone to the point, to the light cone, to the section of the light cone, okay? You can check in the flat case where u is simply minus t plus x dot omega, you can check that you indeed get this distance. Actually, it's slightly different. Yeah, it's not quite true. Actually, it's the distance, sign distance. If you're inside, you have the negative distance, and if you're outside, you have the positive distance. Okay, so now precisely, let me call A int the set where m is strictly negative, Ax the set where m is strictly positive. As you can guess, in the flat case, you get Ax in the exterior and A int in the interior. And now I want to consider these three regions and argue differently in each region. You can also introduce the angle actually where the max is attained, which again is the angle. Okay, for instance, for this point, that would be omega 0 here. The angle omega 0. And then, well, let me not mention about. Let me not talk about this. I mean, it's just, okay, in the exterior region. So the actually most complicated region is the exterior region, and here you had to do additional stuff. But let me not get into that, and let me just stop here for the definitions. Okay, so here I'd like to make before I go to the actually why this works, I just want to point out that this is a robust method for the reason that although I'm showing you that I have an interior region, an exterior region, the light cone, and whatever. I don't need at all to prove any of these statements. I don't need anything besides what is written here, that is A int is m strictly negative and Ax is m strictly positive. I don't need to prove that this is actually exterior to the light cone. I don't need to prove that it's interior to the light cone. I don't need to prove that the light cone is a light cone. Yeah, no, okay. I don't, yeah, okay, no. No, I mean, I don't need to prove that it's regular. I mean, it could be even not convex. You don't need to prove any statement about connexity. You don't need to prove that this angle here is achieved because it's the maximum of a continuous function, but you do not need to prove that there is exactly one, which is the case in the flat case. I mean, maybe these statements I could actually prove it, but I'm happy to avoid these issues. You really don't need that. Okay, so now let me conclude with why you can obtain a lower bound for phi. So that will be my last slide today. Okay, so let me first say that the interesting point is the proof is already non-trivial in a flat case. It's actually interesting to do the proof in a flat case, and that's how you understand how it works in a curve case. And also, I'd like to say that the reason why you use less regularity is because the only thing you use is actually the fundamental theorem of calculus. Here, the difficulty is, so you're going to use the fundamental theorem of calculus along curves, and the difficulty is to choose what are the correct curves and how you define these curves. So let me be a bit more specific. What are these curves? So I want to, yeah, probably let me this. Okay, so what are these curves? So for instance, so let me just project in sigma s. Well, no, okay, no, actually not. I need that. Okay, so for instance, what is the curve? So if I have a point on the light cone, then the curve, it's very easy. If my point sy is here, so if that's fy, then the curve, it's very easy. It's just this. It's just the generator of the cone that goes up to sy. So it's the null geodesic from Tx which goes to sy, which exists because by definition this is the union of all future null geodesic intersecting S. So that's, then if I'm in the interior, so that's the curve that I call eta, right? That's what I call eta. Now, if I'm in the exterior, I will have an eta 1 and an eta 2. For instance, if this is my omega naught, which realizes the minimum of the distance, then, well, okay, it doesn't look like the minimum of the distance, but nevertheless, okay. So this is what you would use. You will use eta 1 and eta 2. And finally, if you're in the interior, I mean, it's the same, I mean, you can guess that it's the same kind of construction. So if you're in the interior, you're going to, I mean, here, of course, I'm drawing what happens in the flat case. In the curve case, you don't have any explicit representation of these curves, but they are thought as analog of the flat case, of course. Eta 1, eta 2, that's for Sy in the interior. Okay? So now what I call, just using the fundamental theorem of calculus, is the fact that I'm simply going to look at, so for instance, if eta is parameterized by sigma from 0 to 1, I'm simply going to say that I'm going to evaluate u at sigma, u at 1, sorry, minus u at eta of 0, and I'm going to say that this is the integral from 0 to 1 of g of, well, of the derivative of u of eta, which is d of du evaluated at eta of sigma. Well, okay, let me write in the next line. So this is equal the integral from 0 to 1 of g of du of eta of sigma omega times eta prime of sigma d sigma. Okay, this is the only thing I'm going to use. I'm going to relate u at 2 points on the curve, and you see I just have to relate this with this. So essentially, for instance, here, I just relate this to this. So I just apply one time the fundamental theorem of calculus, and I just have to estimate this integral. And the point is that this only requires u to be null du to be null infinity. So that requires only du to be null infinity. And here, I claim that you can do so in other words, this is perfectly fine. The only problem is this one is what this requires you. What it is that is required. So in other words, I'm going to shoot my curves. So in other words, I'm going to be at the point here, I'm going to shoot my curve to go to Sy. And I claim that I can realize this curve in the curve case such that this belongs to the span of d omega n. So in particular, this depends only on one derivative in omega, one derivative in x. Okay, so that's where you see the condition that you only need one derivative in x, one derivative in omega. Okay, so that's the point. Okay, so let me maybe, maybe I can take two more minutes. Okay, okay, so let me finish in 2 minutes. So here, well, let me give you one example, and then I'll just finish with these 2 points here. So one example, I want to give you the simplest example, the case where the point is on the light cone and in the flat case. So I'm taking the flat case. I'm taking flat case with because I want to show you how you get this estimate with t minus s omega minus omega dot square. I want to show you this lower bound here. So let me take the flat case. And let me take with Sy, which belongs to the null cone, Okay, so in other words, I'm here, I'm on the null cone, and this is my curve. So what is my curve? So now I'm saying that I have only one curve, and I'm saying like u Sy omega is equal to u of minus u of tx omega, and I just have to use. So my curve goes from, it's parameterized by time, so the time goes from t to s. Then I have the Minkowski matrix, so I have m. And then I have the derivative of u. So derivative of u is minus 1 omega in the flat case. And then I have the derivative of my curve, but my curve is the curve which goes from this, it's the null geodesic in the flat case, which goes to angle omega 0. So it's simply minus 1 omega 0. Actually, I think it's plus 1, right? What am I doing? Sorry, it's plus 1, it's plus 1, right? Okay, so this is derivative of u, and this is eta prime. Okay? And now, if you take in Minkowski spacetime, what is this? This is simply minus 1 plus omega dot omega 0. And this you can immediately compute because omega is on the 2 sphere. This is and omega 0. This is I think it's minus omega 0 square divided by 2. Okay. So in other words, from the integration in time, you get the t minus s, and from the dot product, you get omega minus omega 0 square, and hence you get the correct lower bound. Okay. So that's the simplest case, but I think it's very easy. I mean, the idea, again, I mean, frankly, the idea, if you understand in the flat case, you understand in the curve case. And sorry, where's my, okay? Okay, so now let me conclude with 2 remarks. So first of all, why do I need this global coordinate system? That's because I need to make sure that when I shoot my curve, it goes to the right point. In other words, if I want to end up in Sy, I'm going to go start at omega naught and shoot my curve, and I want to make sure that I end up here, I need to check that in my coordinate system, I get the right coordinates of Sy. So the point is that you always have one coordinate which is right, and then you shoot along the other one. You keep one coordinate constant, and you make the other vary. And this is why this shooting procedure which forces your derivative to be spanned by d omega n and n. And then finally, where do you use these bounds on n omega minus n omega prime and d omega b and b? Well, actually, the point is you get the same thing as in the flat case, except that you start getting the difference between what you get in the curve case and the flat case. So what you get is b minus 1 d omega b and n omega minus omega prime. And so the difference between the flat case is that you pick additional O of epsilon terms. So for instance, instead of getting a lower bound by 1/2, I mean, it just changes the constant here, but for epsilon small enough, you still get a positive constant. Okay, so that's all. Okay, I'll finish here.